Hello everyone, I'm Bittu Singh and this is our fourth tutorial. So we'll solve those problem. It is based on change of basis, and another thing is linear functionals. So let us see our first problem. Okay, so here T be a linear transformation on F31. So linear operator on F31, linear transformation from V2 itself is called linear operator. So here it is F31 to F31. So if is a field, and Tx it is given as A times X, where the matrix A is given by this. And now two sets of bases are given. One is the standard basis, it is 1 0 0 0 1 0 0 0 1. Another is this alpha 1 2 alpha 1 dash alpha 2 dash alpha 3 dash. Those are two ordered bases, and now it is given that alpha any element of F31, that is any vector, so its coordinate with respect to this b dash, it is given as x dash, and coordinate with respect to b, it is x. Now the question is, what is the relation? That is, so what is the relation between x and x dash? And another thing is matrix representation of the operator T with respect to the basis b dash. So let us solve this problem. So for those type of question, first we'll write the b dash, that is element of b dash, in terms of element of b. For example, let us take alpha 1 dash, it is 1 1 1. It can be written as 1 0 0 plus 0 1 0 plus 0 0 1. So this, you can see that those are standard bases, and by this notation those are alpha 1 alpha 2 alpha 3. So we can write it as alpha 1 plus alpha 2 plus alpha 3. So alpha 1 dash is same as this combination. Similarly, alpha 2 dash, we can write alpha 2 dash, there are only two 1 1 on the first and second coordinate. So alpha 2 dash, this can be written as alpha 1 plus alpha 2, and there is nothing, alpha coefficient of alpha 3 is 0, so 0 times alpha 3. And we note that alpha 3 dash is same as alpha 1 itself, right? So we can write alpha 3 dash as alpha 1 itself, and other thing are 0. So 0 times alpha 2 plus 0 times alpha 3. Therefore, if coordinate of so here we see that coordinate of alpha, any vector with respect to b dash, this is x dash, and with respect to b, this is x. Then the thing is that x can be written as x equal to p times x dash. This p is obtained from this coefficient. Okay, so here we can see from here the coefficient. If we take the coefficient, so coefficient of the first thing is sorry, let me write. Coefficient of the first combination are 1 1 1. So we put 1 1 1 on the first column. Similarly, coefficient of the second vector alpha 2 dash, it is 1 0 0. Here 1 times 0. So let me explicitly write 1 1, and here also 1 1 1. So coefficient in the second, coefficient for the second is 110. So we put 110 in the second column. Similarly, 100, this combination we put it in this third, sorry, it is 100 now, and earlier it was, oh, it is 110, and now for the third combination we have 100. So P will be given by this matrix. But if we see in the first option, P will not look like this. So this is not the answer. Similarly, for the second, first column start with 111, but here 100. So this is also false. So two options are discarded. Now let us see what about other. We need to write matrix representation of the transformation with respect to B dash. And we know that with respect to B, it is already given. With respect to B, the matrix representation is A. So we write in this notation T with respect to B, it is already given A. And what is A? 1 0 minus 1. First row is 1 0 minus 1. Second row is minus 1 2 1. Sorry. And this is 0 0 1. Now we know that if we change the basis from B to B dash, then matrix representation will change. And the matrix representation, it is given by P inverse AP. Okay. So the P is this matrix. Sometimes this matrix is called change of basis matrix. Okay. This matrix sometimes called change of basis matrix. So what we are really doing, we are applying P so that it makes to from here we can see that if we apply P on the new coordinate, then it will take us to the old coordinate, right? So that's why there is P, and we apply A because A is transformation with respect to the old coordinate. Now we need to again come to the new coordinate, so we again apply P inverse. So that is the motivation for those type of similar matrix. Okay, so this is the matrix representation with respect to the new basis B dash, and it is obtained from this change of basis matrix. Okay, so we have P, but we need to find what is P inverse. How do we find P inverse? We successfully apply row reduction on P I, this thing, right? But what is Pi? If we put together, it is 111, 110, 100, and then identity matrix 100, 010, 001, and we'll apply row reduction, and we want to make it identity, right? So the first thing we can perform R1 minus, maybe darker, R1 minus R3 and R2 minus R3. So it will make 0, and then 1 1, then R1 minus R3. So R1 minus R3 will make it 1 0 minus 1. Similarly, R2 minus R3, it becomes 0, and after that it is 1 0, then 0 1 minus 1, and R3 is unchanged, 1 0 0 0 0 1. Now the next step will be R1 minus R2, right? So R1 minus R2, it will create 0 0 1, 1 0, sorry, 1 minus 1, and those are cancelled, so it is 0. Then everything is unchanged. After this, what we can do, we just exchange R1 R3, right? Exchanging R1 R3, it will give you identity matrix on the left side, and now R1 is 0 0 1 because we have exchanged those two rows. So it is 0 0 1, and R3 will be 1 minus 1 0, but R2 is unchanged. So this is the inverse, right? This is, sorry, P. Notation is P. We have started with P, so we will get P inverse. And left side it is identity. This is the required P inverse. So we got the P inverse. P inverse is 0 0 1. Let me write here. So it is 0 0 1, 0 1 minus 1, and after that 1 minus 1 0. This is P inverse. And A is also, we also have A. Let me copy it. Paste. Sorry. How can we do it? Okay. So maybe how to copy. Copy. Okay. P inverse A, and now again we'll put P. So P is already there. So it is 1 1 1, 1 1 0, 1 0 0. Now we'll simply multiply those two matrices. So P inverse is fixed. We multiply those two matrices first. 0 1 minus 1 0, 1 minus 1 0. So if we multiply, then first column will be addition sum of those three columns. So it is 0, 2, and 1. Second column is R1, first column plus second column, because of this 1 1 appear here. So it is 1 1 and 0. Third column will be the third column of them. Sorry, first column of this thing. So it is 1 minus 1 0. So you can multiply and you will get this answer. Now again we will multiply those two things. So what is the answer? First thing will be the third row, because 0 0 1 appeared on the first row. So third row will put third row, and second row will be just R1 minus R2, which is minus 2, 0, plus 2. Someone's mic is on. Do you want to say something? Okay, maybe turn. Then what is the third row? Third row is, what we have done, it is second minus third. So it is, sorry, second minus third means it is 1. Then 1 minus 0, 1, minus 1, and after that R1 minus R2, which is same as minus 2, 0, plus 2. So this should be the answer. Let me check if it is matching with something. So let me put the answer here. So can we verify that the answer T with respect to B dash, it is matching with this answer, right? Matching with this answer. So this is the correct answer. 1 0 0, 1 1 minus 1, minus 2 0 2. Okay. Now problem number 2. Just make it bigger. Okay, can you see that? Okay, so here W is the subspace of R5, and it is spanned by those vectors alpha 1, alpha 2, and alpha 3. So W is spanned by those three vectors. And now W naught. So what will be the basis of W naught? So what is W naught? W naught is the annihilating polynomials. Polynomials which annihilates those points, right? Uh, Now the question is W naught. The basis of W naught is given by F1, F2. Then uh, which are the correct possibility of F1, F2? So let me write the solution. So let me recall what is W naught. W naught, it is a function f which is a map from R5 to R such that, so W naught is linear function. It will look like some Ci xi, right, where I equal to 1 to 5, which satisfy the condition that f applied on alpha 1, that is f annihilate alpha 1, which is 0, f annihilate alpha 2, which is 0, and also f annihilate alpha 3. So this is the W naught. Now we need to find what is the possibility of those functions f, those linear functions. So let me solve in this way. So let f belongs to W naught, right? If we assume f belongs to W naught, then f satisfy the relation f at alpha 1 is 0. That means what is the meaning of this? That is C1. What is alpha 1? Alpha 1 is same as 1 to 1, 0, 0. So if we write fx, this is same as C1 x1 plus C2 x2 plus C3 x3 C4 x4 and C5 x5. Now f of alpha 1 equal to 0 and alpha 1 is same as 1 to 1, 0, 0. Alpha 1 is same as 1 to 1, 0, 0. That is, we may put f at 1 to 1, 0, 0. This is given because f annihilates alpha 1. So what is the implication? We'll get the relation C1 plus 2C2. We are putting 2 here and similarly 1 here, which will give you C3, and then everything is 0. So it is 0 times C4. We are putting the value of the coordinates, right? Plus 0 times C5. This is given as 0. Similarly, f satisfy the other relations, that is f annihilates alpha 2, f annihilates alpha 3. If we put those things, then we will get, so alpha 2 is 0, 1, 3, 3, 1. So alpha 2 is 0, 1, 3, 3, 1. Then similarly we can get the relation 0 times C1. This will give you the relation 0 times C1 plus 1 times C2 plus 3 times C3, 3 times C4 plus 1 times C5. This is 0. Similarly, if we put the value alpha 3, 1, 4, 6, 4, 1. Then this gives the relation 1 times C1 plus 4 C2 plus 6 C3 plus 4 C4 plus C5 equal to 0. Now we need to find those kind of polynomials. So what are the possibility of those polynomials which annihilates or kills those coordinates, those alpha 1, alpha 2, alpha 3. So we need to find those coefficient actually, C1 up to C5. So let us find. So how to find those C1 up to C5? Just solve those three equations. So to solve star, and we know how to solve those kind of equation. It is just by row reduction, right? We put those things in row and we'll reduce. So 1 2 1 0 0, and after that 0 1 3 3 1. Similarly 1 4 6 4 1. Apply R3 minus R1. So everything is same, but the third row becomes 0 in the first place, and after that 2 5 4 1. Now what can we do? We just, to remove these 2, we apply R2 minus 2 R1. Similarly, to remove these 2, we apply R3 minus 2, sorry, R2. R1 minus 2 R2. And similarly, R3 minus 2 R2. We just subtract the second row. So, second row is unchanged, 0 1 3 3 1. But first row becomes 1 0 here. Now 1 minus 6, which is minus 5. 0 minus 6 minus 6. 0 minus 2 minus 2. And now if we see this row, then what can we see? That this is the third row minus 2 times the second row. Third row minus 2 times the second row. It will give us 0 0. And now 5 minus 6, which is minus 1. And 4 minus 6, which is minus 2. And 1 minus 2, which is minus 1. Now again we will perform the operation. So what can we do? We just remove those minus 5 and 3 here. So it is R1. First, let us multiply by negative sign. So R3 minus of R3, which will give you 0 0 1 2 1, and everything is fixed. That is 0 1 3 3 1 1 0 minus 5 minus 6 minus 2, and the next step is R1 plus 5 R3. So it makes minus 5 pennies, and similarly R2 minus 3 R1, it will make these 3 pennies. So we'll get identity matrix on the left side, 1 0 0 0 1 0 0 0 1. And now, so other thing is R1 plus 5 R3. So minus 6 plus 10 is 4, minus 2 plus 5, it is 3. Similarly, R2 minus 3 times R1, sorry, 3 times R3. So R2 minus 3 times R3, so 3 minus 6 minus 3, and 1 minus 3, which will give us minus 2, and everything is fixed. So from here we can easily now, since this is row reduced echelon form, we can easily solve the system. That is, we know that Ax equal to 0, this is equivalent to Rx equal to 0, where R is the row reduced echelon form. So we can now easily solve the equation. So here X means we have taken those to the those things as unknowns, C1, C2, C3, C4, C5. So we can easily see that the fourth and fifth column, those does not contain any leading one, so those are free. So this is free column, and similarly this is free. So to get to linearly independent solution, so we can also see that rank of this matrix is 3, and it is clearly 3 by 5 matrix. So there are number of linearly independent solution. This is same as 5 minus rank, and rank is same as 3, which is 5 minus 3. Therefore 2. There will be 2 linearly independent solutions. So we can, fourth and fifth column are free. So we'll choose those things as fourth and entries in the fourth and fifth column. So this is 1 0 and another choice will be 0 1. So if we choose those combination, then those above 3 coordinate is automatically determined. So we'll get the solution. Now if we choose 1 here, 1 to be the third, 1 corresponding to the third thing, then what is the third equation? It is simply C3 plus 2C4 plus C5 equal to 0. But we have chosen C4 as 1 and C5 as 0, right? Therefore, from here we can easily see C3 will be minus 2 because C4 is 1 and C5 is 0, right? So from here we can easily see this will be minus 2. Similarly, this thing will be plus 3 and first coordinate will be minus 4. Just apply those computation. It is easy to get. Just change those signs. So it is minus 4 and this becomes plus 3. Similarly, if we choose 0 1, then the corresponding those equation, this will give us, here it is 1, so we'll put minus 1 here. It is minus 2, so we'll put plus 2 here. And it is 3, so we can put minus 3 here. So those are the solution. Okay. So let me compare. Therefore, those are the values of C1 up to C5, linearly independent choices. But we initially we are finding the linear, that is linear polynomial. That is F1 will take this forms, combination of those Ci xi. Therefore, F, which is Ci xi, summation of Ci xi, it will take two form. If we choose the first thing, then we will get F1, one polynomial, linear polynomial. It is minus 4 Cx1. Value of C2 is now 3. So plus 3x2. Similarly, minus 2x3 plus x2. And from this second thing, we'll get another function, linear function, which is minus 3x1 plus 2x2 minus x3 0x4 plus x5. So those should be two possible solutions. There are more solutions, but everything can be determined as linear combination of these two. So let me see if this is matching. So this should be the answer. And now we can see it is matching with minus 4 plus 3 minus 2x3. So either minus 2x3 plus x4 plus x4. So B is the correct answer. Okay. So let me solve another problem. Problem number 3. Okay. Again here this B is standard basis 1x x square x cube. Standard basis of the polynomial space. Polynomial, B is the polynomial with degree less equal to 3. Now for any polynomial Px and the operator from V to V, it is given as differential D. So we know how can we difference, how can we operate with D. For example, D of 1, it will give us 0. D of x, it is 1. D of x squared, this is 2x. D of x cubed, this is 3x squared. So this is the linear operator. Now D applied on P, this is same as change of basis matrix, and D applied on P with respect to coordinate with respect to B dash. Okay, we have given two coordinate and there is a comparison or relation. So this coordinate, it is given by P times the coordinate with respect to B dash, and this P is also given. Now the question is, what will be B dash? Okay, so to solve this problem, from here we can see that DE with respect to B, this is same as dP with respect to B dash, but there is P, right? And if we see 1, what is the coordinate of 1 with respect to B? It is simply 1 0 0 0. It is 1 0 0 0. Similarly, coordinate of x with respect to B, it is 0 1 0 0. X square with respect to B, 0 0 1 0. Similarly, we can write all those coordinates, right? X cube with respect to B, it is 0 0 0 1. So we want to find B dash. So how can we find B dash? It is just apply P on those E1, E2, E3, E4. So P applied on E1 1 0 0 0, it is same as 1 0 0 0, 1 1 0 0, 1 2 1 0, 1 3 3 1, applied on 1 0 0 0. So it is same as first column, 1 0 0 0, right? Similarly, P applied on 0 1 0 0, this will be the second column, 1 1 0 0. P applied on 0 0 1 0, this will be the third column, 1 3 3 1. P applied on 0 0 0 1, this is fourth column, 1 3 3 1. Okay, so we have all those information. What is the what is the thing which is obtained by applying P? Now P applied on 1 0 0 0, this gives 1 0 0 0, but what is the matrix? Suppose, what is the polynomial A? So we have chosen A. Yes. So what is the polynomial C0 plus C1x plus C2x squared plus C3x cubed, whose coordinate is 1 0 0 0? It is clear, right? This should be 1. So this matrix corresponds to 1, that is coordinate of 1. This is actually 1 0 0 0. Similarly, if we see 1 1 0 0, this is actually coordinate of 1 plus x, and this third thing, it is coordinate of 1 plus 3x plus 3x square plus 3x square. Coordinate of this with respect to standard basis. And fourth, this is actually 1. Oh, those are same. Third thing will be 1 2 1 0. This is wrong actually. 1 2 1 0. So this is 2 and this is actually 1. 1 2 1 0. Now this is actually coordinate of 1 plus 3x plus 3x square plus x square. So those will be the actual solution. So if we compare, first one is 1, then 1 plus x, 1 plus x, then 1 plus 2x plus x square. Sorry, there is 0, there is actually 0. 1 plus 2x plus x square. So this is okay. Then 1 3 3 1. So this C will be the correct answer. Okay. So again, how do we solve those kind of problem? First, simply we apply those P on the standard matrices 1 0 0 0 and 0 1 0 0 0 0 0 1. If we apply those, apply P on those matrices, we'll get something, and we'll write those matrices. We'll find a linear polynomial, not linear. We'll find a polynomial, degree 3 polynomial, whose matrix representation, that is coordinate with respect to the old basis, give this. If we can write, then those will be the required solution. Okay. So now question number 4. Here T is a map from R3 to R3, and matrix representation with respect to this basis, it is given as this matrix A. Now question is, what will be T applied on 1 0 0, T applied on 1 1 1. So let us solve this problem. T applied on 1 1 1 we can see easily, and 1 0 1 1 0 1 minus 1, 1 0 0 is also there, so we can find those two very easily, because we can see that A is given matrix representation of T with respect to B, and let me denote B to be as, those are alpha 1, alpha 2, alpha 3, those bits. So B is generated by those, that is ordered basis is alpha 1, alpha 2, alpha 3. So clearly we can see 1 0 0, this is actually same as, actually there should be transpose, because of our notation there should be transpose. So 1 0 0 transpose, we can see this is same as alpha 3, right? So this is actually alpha 3. and therefore the coordinate of 1 0 0 alpha 3, that is we can write alpha 3, this is same as 0 times alpha 1 plus 0 times alpha 2 plus 1 times alpha 3. So coordinate of 1 0 0 with respect to this basis, the given basis, it is actually 0 0 1, right? Similarly, we can see coordinate of 1 1 1, it is 1 1 1 is actually alpha 1. So it is 1 times alpha 1 plus 0 times alpha 2 plus 0 times alpha 3. Therefore 1 1 1, coordinate of this with respect to B, this is 1 0 0. Now we can easily find T applied on 1 0 0 and 1 1 1. So T applied on 1 0 0, this is same as the matrix representation, which is A applied on this thing. So A applied on 0 0 1. But what is A times 0 0 1? A times 0 0 1 means it is the third column of A. So third column of A means 0 2 3. So it should be 0 2 3. But the problem is we again need to find coordinate of 0 2 3 with respect to B. So it is not that straightforward, because what is this? Oh, okay, it is okay, because we have applied matrix representation and it is given with respect to this T, this basis B. So it is okay. Now T applied on 1 1 1, it is simply A times, what is coordinate of 1 1 1? It is 1 0 0. A times 1 0 0. So this is the first column. What is the first column? It is 1 1 minus 2. So we are getting 1 1 minus 2 here. Now we need to see what is the value of T when it is applied on 0 1 minus 1. So simply what we can do, we can write 0 1 minus 1 in terms of this alpha 1, alpha 2, alpha 3. That is, we need to find coordinate of 0 1 minus 1. So coordinate of 0 1 minus 1 with respect to, so 0 1 minus 1, coordinate of this thing with respect to B. We need to find this. So this is equivalent to finding a solution of this system. That is, we need to find, that is, this, we need to find C1, C2, C3 such that C1 times alpha 1 plus C2 times alpha 2 plus C3 times alpha 3 is same as this 0 1 minus 1, right? So to find this is equivalent to writing this as same as 0 1 minus 1. So essentially we are solving this problem, linear equation. So again we will what can we do? We write alpha 1, alpha 2, alpha 3 in the columns. So alpha 1 is 1 1 1, 1 1 1, then alpha 2 is 1 1 0, and alpha 3 is 1 0 0. Zero, 1 minus 1. So we apply row reduction, R1 minus R3, R2 minus R3. It will give us 0 1 1 plus 1 and 0 1 0, 1 plus 1, which is 2, 1 0 0 minus 1. Now R1 minus R2, 0 0 1 minus 1, and everything is same. Simply exchange R1, R3, those two rows. It gives identity, and here it is minus 1, 2, minus 1. So we get the solution minus 1, 2, minus 1. So therefore 0, 1, minus 1 with respect to B, this is actually with respect to new coordinate, this is minus 1, 2, minus 1. So we have successfully found the coordinate of 0, 1, minus 1 with respect to this new coordinate system. So T applied on 0, 1, minus 1 with respect to new coordinate, this is same as A applied on this coordinate 1, minus 1, 2, minus 1. But what is A? Initially A was this matrix 1, 0, 0, 1, 1, 2, minus 2, 0, 3. 1, 0, 0, then 1, 1, 2, minus 2, 0, 3, and multiply with minus 1, 2, minus 1. So if we multiply, what we are getting, it is 1, 0, 0, so minus 1, then minus 1 plus 2, which is plus 1, and minus 2, minus 1, then plus 2, 0, and minus 3. Which is minus 1. So this should be the coordinate minus 1, minus 1, minus 1. So this is not same as, this is not equal to minus 1, minus 1, minus 1. So this is wrong actually. Now similarly, there is 0, minus 1, 1. We need to find coordinate of 0, minus 1, 1 with respect to the new system. But we know the answer because coordinate of this is this. So coordinate of the negative thing 0, minus 1, 1 will be the negative. With respect to B, this is simply put a negative sign. So minus 1, 2, minus 1 is there. So from here it is plus 1, minus 2, minus 1. Sorry, plus 1. So similarly, if we apply T on 0, minus 1, 1 and find the coordinate, it will be simply multiply A with this coordinate 1, minus 2, 1. But again we know the multiplication. It is just apply a negative sign. So it is plus 1, plus 1, plus 1 because the answer is already obtained. So this is the correct answer. 1, 1, 1. Okay, all right. So let us solve the question number 5. Here we need to find dual basis of the given basis B. So B is this 1, 0, 1, 1, minus 1, 0, 2, 0, minus 1. 3 vectors in C3. So uh, we can write those tuples. Let me rename those things. So let me give the name alpha 1, alpha 2, alpha 3. So B is ordered basis alpha 1, alpha 2, alpha 3. We need to find dual of those basis element. So what is the dual? So dual of alpha 1, we can denote it by some function f, which is a map from C3 to C, because alpha 1 is an element of C3. So dual will be a linear functional from V to the field F. Here the field is, so in general, if V is a vector space, vector space Vs. Then dual vector space, it is formed by linear functional f from V to the field F, right? So V star is defined to be all functions, all linear functions functional from V to F. So this is the dual space, and given a basis we can find dual basis that is corresponding to every basis. So suppose V is a basis for V is alpha 1 up to alpha n. So from those alpha 1 up to alpha n we can find a basis of V star, which we write as f1 up to fn, corresponding to those alpha 1 up to alpha n. What are the properties? If f1 applied on alpha 1, it is 0. If f1 applied on other thing, alpha I, where I is not equal to 1, sorry, f1 applied on alpha 1, it will give us 1, and if f1 applied on other thing, it will give us 0 when I is not equal to 1. Similarly, f2 applied on alpha 2 only gives 1, and f2 applied on other thing will give you 0. So in general, if we write for alpha I, dual of alpha I as fi, then fi applied on alpha I give you 1, but fi applied on alpha j, so if j not equal to I, this give us 0. This is the definition of dual of alpha I. So those are actually linear functional. Now the question is, what is f1, f2, f3? Okay. So assume, let f1 as ABC, this is as some k1a, those type of combinations, k2b plus k3c. If f1 ABC can be written as this combination, then the thing is given they will have some equation that is f1 times those alpha 1. So what is the value of alpha 1? Alpha 1 is 101, given f1 of 101, this is actually 1, and f1 of other thing, that is alpha 2 alpha 3, which is 1 minus 1 0, and f1 applied on 2 0 minus 1. By definition, those are 0. Definition of dual basis. So similarly for if other thing we can obtain. So what is the combination? We are getting k1, f1 applied on 101, it is giving k1 plus 0k2 plus k3 equal to 1. Similarly, k1 minus k2 plus 0k3 equal to 0. 2k1 plus 0k2 minus k3 equal to 0. So we are finding solution of this equation, right? So we are finding to find, so f1 is obtained by solving the equation. So if we write k1, k2, k3 here, then there is some matrix. So we can write those information as matrix. A times k1, k2, k3 is same as 1 0 0. Similarly, f2, this is actually obtained by the equation A times k1, k2, k3. So everything will be same, but f1 applied on the first thing give you 0. Sorry, f2 applied on first thing will give you 0. f2 applied on the second thing will give you 1. F2 applied on the third thing will give you 0. So this is same as solving this equation 0, 1, 0. Similarly, F3, the third functional, this is obtained by solving a times this k1, k2, k3, which is 0, 0, 1. So we need to find solution of those equations. So together, if we put together, we are finding the finding solution of those things. That is how to find a solution of those kind of system. Simply we will put a and we put those augmentation, right? So we can put all those things together also. So first one is 1, 0, 1, 0, second one is 0, 1, 0, and third one is 0, 0, 1. We can see this is actually identity matrix. So essentially we need to find inverse of A here, right? So those column will give us the correct solution. So if we put A, so what is actually A? From here we can see that those coefficient matrix A, coefficient matrix, it is same as 1, 0, 1, 1 minus 1, 0, 2, 0, minus 1. So we put this is same as 1, 0, 1, 1 minus 1, 0, and third row is 2, 0, minus 1. After that, everything is identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So we'll perform the operations. So first thing we can perform R2 minus R1 and R3 minus 2R1. It will give us so is everything correct? 1, 0, 0, okay. So 3 coordinate, everything is okay. 1, 0, 0, 1, 0, 1. First row is unchanged. R2 minus R1, subtracting first row it 0 and minus 1, 0, minus 1, minus 1, minus 1, 1, 0. And similarly R3 minus 2 R1, it gives us 0, then 0, and minus 1, then minus 2, which is minus 3, and this minus 2, 0, and plus 1. So after that, we can simply perform so minus 1/3 times R3. Everything is same, but the third row will change. So third row becomes 0, 0, minus 1, minus 2/3, 0, 1/3. Now the operation will be, so we can delete those 1 and minus 1. So we perform the operation R1, sorry, we have taken negative, so this is plus 1/3, this is plus 2/3, and this is actually minus 1/3 because minus 1/3 times R3. Now we can subtract R3 from R1, and similarly we can add R3 with R2. So this will give 1, 0, 0 here, and R1 minus R3. So it is 1 minus 2, 1 minus 2/3, which is 1/3. So 1/3, 0 minus 0, 0, 0 plus 1/3. So it is 1/3 again. So after that it is 0 minus 1 and 0 here. Now minus 1 plus 2/3, which is minus 1/3. 1 plus 0, which is 1, and 0 minus 1/3, which is minus 1/3. Similarly, the third row is unchanged, 0, 0, 1, 2/3, 0, minus 1/3. Now the last step will be simply change the sign. So we make those sign opposite so that left side becomes identity. So it is plus, it is minus, it is plus. So this is the row reduced echelon form. So we already found the solution. So the solution, therefore, the solution of the first equation, a times k. So we may write those things as a times. Let me denote the symbol k to denote this vector k1, k2, 3. A times k is 1, 0, 0. So what is the solution of this thing? This is same as this row reduced echelon form times that k is same as 1/3, 1/3, 1/3. But row reduced echelon form is identity itself. So r times k is same as k. So the solution of the first equation is 1/3, 1/3, 1/3. Similarly, solution of the second equation will be given by second column. So those are the actually solutions. This, and this three thing gives the solution. Okay, maybe if we denote it by 1, 2, 3, then 1, 2, 3, those are actually solution of 1, solution of 2, this is solution of 3, right? So plus 1/3, 1/3, 2/3. But what we are really trying to, what we really tried to find, we are trying to find this f1. F1 is same as k1a plus k2b plus k3c. But this k1, k2, k3 is given by the solution of the first equation. So solution of the first equation is 1/3, 1/3, 2/3. So f1 is same as 1/3, 2/3, 1/3, 1/3, 2/3 plus 2/3 x1, x2, x3. Right? F1, x1, x2, x3 is given by this equation, or maybe ABC, because ABC. So it is better to write ABC. It is A A, B, C. So together we can write as A plus B plus 2C by 3. So first solution will be A plus B plus 2C by 3. Similarly, it is easy to see all the other cases. F2 ABC, it is simply obtained from the coefficient of the second column, which is 0 times A minus B plus 0 times C. So the result will be minus B. Similarly, F3 times ABC, this obtained from the third column, which is same as A plus B minus C by 3. So those will be the answer. A plus B plus 2C by 3, A plus B plus 2C by 3, everything is okay. Second one is minus B. Yes, second one is minus B, and third one is A plus B minus C by 3. So this is the A plus B minus C. So option A is the correct answer. Everything is matching. Up to this, is there any doubt? Question 5. Okay, if not, okay, thanks. So if not, let's start question number 7. So again, T is a linear operator on R3. Linear operator means domain and codomain are the same vector space. So T is a map from R3 to R3. And the definition of T is given as TABC is same as A, 0, B. and ordered basis, this ordered basis is given. So we rename it alpha 1, alpha 2, alpha 3. This is the ordered basis. So instead of doing this, let me say what we have already done in this question. So we actually found all those. We can see that if you already know inner product, otherwise it is okay. So we are finding those k1, k2, k3, so that it makes those equation 1 0 0 0 1 0 and 0 0 1. So you can start from this step. Actually you do not, you can start from this step. It is okay to solve those type of problem, those type of MCQ question. It is okay to start from this step and simply perform row reduction, so that you get this column. From this column the answer is ready. You don't need to see anything else. Those are obvious, right? This will give you a plus b plus 2c by 3, similarly minus b, and similarly a plus b plus minus c by 3. So you solve in this way. You don't need to write those type of steps, otherwise it will take lots of time. So back to this question here, the basis, ordered basis b is given alpha 1, alpha 2, alpha 3, and the question is which of the following statement is correct. So we need to see what is the t transformation with respect to this ordered basis. So again we first see the transformation t with respect to the old basis. T ABC is same as A0B. Therefore from here t applied on, so let the notation b is already there, so we may write b0, the initial old basis. Old basis is the standard basis e1, e2, e3. Now t applied on e1, e1 means 1 0 0. It is same as 1 0 0, which is e1. T applied on e2, 0 1 0. E2 means 0 1 0. So t, which is same as 0 0 1 by this definition, but this is same as e3. So we may write, let me again write t 0 0 1, that is t of e3. This is same as 0 0 0 by this definition. So from here it is clear that t e1 is same as e1 plus 0 e2 plus 0 e3. T of e2, this is 0 e1 plus 0 e2 plus 1 times e3. T of e3, this is 0 times e1, 0 times e2, 0 times e3. Therefore matrix representation of t with respect to old basis b0, it is same as just put those entries in column. So for example, first entry, you can see the first entry is this, so we put in the first column. Second entry is this coefficient, so we put the coefficient in the second column. The third we put in the third column. So the final answer will be, not final answer, this representation, matrix representation, it is 1 0 0 0 0 1, and the third column will be 0 0 0. So this is the matrix representation. Now we need to find matrix representation with respect to the given basis. So again, what is the step to do those type of problem? We write b in terms of the standard basis, right? So b here alpha 1, it is easy to see that alpha 1, which is 1 minus 1 1, 1 minus 1 1. So you can write it as 1 1 times e1, 1 times 1 0 0 minus 1 times 0 1 0 plus 1 times 0, 0, 1. So it is actually E1 minus E2 plus E3. Similarly, we can write other thing also. Alpha 2. Alpha 2, we can see alpha 2, it is same as minus E1, minus sign in the first coordinate, then plus E2 plus E3. Similarly, alpha 3, which is 1, 1, 1, is same as E1 plus E2 plus E3. From those data, what can we so we first write change of basis matrix. Okay, so from here change of basis matrix, which is P is same as, so again we put those datas in the columns. So it is 1 minus 1 plus 1 minus 1 plus 1 plus 1. Then the third is, so let me, so third will be third here. So it is plus 1 plus 1 plus 1. So this will be the change of basis matrix. This is the second, and first one is there. So now transformation with respect to the given basis B, it is simply P inverse. Transformation with respect to old basis times transformation times P. That is, if you denote it by A, then this is simply P inverse AP. Similar matrix. Now, so again we need to find what is the inverse of P. So let me find inverse of P. Similar kind of calculation. It is 1 minus 1 1 minus 1 1 1 1 1 1, and we put 0 identity here. So we take the matrix of this from Pi. So it is 1 0 0 0 1 0 0 0. So we apply row reduction. So maybe R2 plus R1 and R3 minus R1. So first row is fixed 1 minus 1 1 1 0 0. Second row is 0 0 and 2 1 1 0. Third row is 1 minus 1, which is 0, 1 plus 1 2, 1 minus 1 0, and then minus 1 here 0 1. Now half of R2 half of R3. So just take half of those things and exchange. We are also exchanging. We are not writing in separate way. So we also exchange those two rows. So this will give us 0 1 0, and this is minus half, corresponding to the third row, minus half 0 plus half, and corresponding to the second row we get 0 0 1 and half half 0, and first row is fixed 1 minus 1 1 1 0 0. And what is the next step? It is R1 plus R2, so that this minus 1 get cancelled, and R1 minus R3, so that the third minus 1 get cancelled. So we'll get identity on the left side, and R1 plus R2 minus R3. So 1 minus half plus half minus half, which is 0. Similarly, R1 plus R2, 0 minus half. Similarly, 0 plus half minus 0 plus half. So this is the solution, minus half 0 plus half, half half 0. So we may write, this is actually P inverse. We get I and P inverse together. Okay. So P inverse is given by 0 minus half half. 0 minus half half. After that, minus half 0 half. After that, half half 0 times AP. So what was A? A was 100 001 000 100, then 001, then 000 times P. I am not writing. So first multiplying those two, we'll get the first column. First column is 0 minus half plus half, and the third column, because there is 001, third column is half half 0, and the third column will be 0 times those things, so it is 0 times P. And now what is the value of P? P is 1 minus 1 1 minus 1 1 1 1 1 1. So now again we need to multiply those two things. So it is first row is 0 times half of the second row, which is minus half plus half half. And now similarly the third row will be half of the first row. It is half minus half plus half. And now we need to see what is the second row will be so minus half minus half minus half, which is minus 1, then plus half which is 1, then minus half plus half which is 0. So this should be the solution. So let me copy and verify if it is matching with something. So we can see minus 1 1 0. So up. So this is the solution which So we can see the option B matches with our solution. So option B will be the correct answer, but it is not. There can be multiple correct answer. So we also can see that T is T of ABC is A0B. So ABC, if we apply T, we are getting A0B. Now, if we again apply T, what will get? So, what is the meaning of T? T making the second coordinate 0, and first coordinate remains same, which is A here, and the third coordinate, it is obtained from the middle, right, by definition of T. So the third coordinate will be 0. So from here, T square is not, this is actually T square. So T square is not T, because T and T square are different. T of ABC, you can see T of ABC, which is A0B, which is not same as T square ABC, because T square ABC is same as A00. So those two are different. So T square and T are not same. T square equal to A00. This is correct. There should be ABC here. Otherwise, it is not making any sense. So T square ABC is A00. So option B and D are the correct answers. So let me solve question number 8. Okay, question number 9 here. So here S be a linear operator on R2 such that S square equal to S. Then S can take which of the following form? Clearly, if we take S equal to 0, then 0 square is same as 0. So this equation is satisfied by the first option. So this S can take the form 0, and also if we take S equal to I, we can see I square identity square gives the same identity. So this can be an answer. And Now if we take this 1 0 0 0 s to be this, then a square, this is same as 1 0 0 0 times 1 0 0 0. So this is same as 1 0 0 0. So again we are getting a square to be s. So ABC are the choices, that is s can take those forms. So ABC are the correct answer. D is not correct. Question number 10. Here T and U are linear operator. So T and U are operating on R4. Those are linear transformation from R4 to R4. T is given by this equation and U is given by this equation. Now the question, what are the possibility? That is, so we can see that ABCD, if we apply T, it is just shifting one right. So it is 0, then ABC. Now again if we apply T, it will again shift one right. So it is 0, then again 0, then AB. So T, which will make it 0 0 0A. So those are the actually correct notation. And again if we apply T, one right shift, it will make it 0. Okay, so from here it is clear that t to the power 4 equal to 0, right? And also it is clear that t cube is non-zero, because t cube, this is the t cube ABCD. If we apply t cube on ABCD, we are getting 0 0 0, which is non-zero. For example, take A to be 1, you will get non-zero thing. Therefore, since A is the matrix representation corresponding to this transformation T with respect to standard basis B gives us A. Therefore, it is clear that A to the power 4 equal to 0, because standard matrix representation also satisfies the same relation. Okay, so A to the power 4 equal to 0. If T is 0, then matrix, because there is a theorem you can look at, that matrix representation of T maybe T1 T2, T1 times T2. This is same as matrix representation of T1 times matrix representation of T2. So from here it is clear that since T to the power 4 equal to 0, their matrix representation also will be 0. Similarly, we get 0 as a matrix representation. It is only possible when it is 0 itself. Okay. So from here it is clear A to the power 4 is 0 and A cube is non-zero. This will imply A cube equal to is not equal to 0. And now let us see. So it is clear that A to the power 4 equal to 0 is correct and A cube is non-zero, it is also correct. Let us see what is happening when we apply U. U of ABCD, this is same as BCD 0. BCD 0. So what is U doing? U is making a left shift. ABCD, if we apply U, we are getting BCD 0. U squared, sorry, again U, another left shift is CD 0 0, U D 0 0 0, U 0 0 0 0. So from here it is clear that u to the power 4 ABCD, let me write u cube. U cube is this thing, three operation of u. This is giving us D000, and u to the power 4 ABCD is actually 0 for all ABCD. Therefore, it is clear that again matrix representation of u with respect to the basis B, it is written as B, capital B. Okay, this is actually script B. So from here it is clear that B cube is non-zero, but B to the power 4 is actually 0. So this is also true. B cube is non-zero and B to the power 4. So those two options are correct. Now the question is, what is the relation between those two matrix representation? So T of ABCD and U of ABCD. So again, write T ABCD. The by definition this is 0 right shift, 0 ABC. So if we apply T on 1 0 those basis element, it will give us 0 1 0 0. Similarly, T applied on E2, this is actually E1. T applied on E2, this will give us this is actually E1 itself. This will give us 1 here and everything is 0, that is 0 0 1 0, which is same as E3. Sorry, this is E2. T applied on E3, this is 0 0 0 1, which is same as E4. And T applied on E4, E4 means 0 0 0 1. So if we apply T on using this definition, then it will give us 0 0 0 0, because we are simply doing right shift. So one right shift will make it 0, because it is 0 0 0 1. So one right shift, it will make it 0. So this is actually 0. 0 times E1 plus 0 times E2, 0 times E3 plus 0 times E4. Similarly, this is actually 0 times E1 plus 1 times E2 plus 0 times E3 plus 0 times E4. So matrix representation of T with respect to standard basis, so we put those coefficient on the first column. Okay, so what are the coefficient? Which is 0 1 0 0. Similarly, here we can see that coefficient will be 0 0 1 0. So 0 0 1 0. Similarly, here coefficient is 0 0 0 1, and on the last coefficient is 0 0 0 0. So matrix representation of T with respect to the given basis is this. And similarly, matrix representation of U with respect to, we need to find matrix representation with respect to the this given basis. So yes, okay. So if we write U, it is clear, right? You even don't need to do those steps. You can simply put simply see those things from here. That is, multiplying ABCD will give you this equation 0 ABC. Okay, if you multiply this with ABCD, you will get this equation 0 ABC. You can verify simply. That is, first thing is 0 because there is 0 rows. Similarly, the second thing is A, which is A. So you can see this is the correct matrix representation. Similarly, U with respect to the basis B, it is simply what is the correct representation 1 0 0 0, this goes to 0. So this is 0 0 0 0. Similarly 0 1 0 0, this goes to 1 0 0 0, and after that 0 1 0 0 0 0 1 0. It is, you can easily verify this is the matrix representation, because if you multiply with ABCD, you will get the same thing, BCD. BCD transpose, but yes. Okay. So you have already those two matrix representation which are denoted by AB, and we need to check if A and B are similar or not. That is, A can be written as P inverse BP. So let us see. So we start with B and we'll perform symmetric row reduction, so that it gives us A. So maybe row reduction, we can see that exchanging those rows will can give us A. So let me see if it is possible or not. So 0 0, the last row contains 0 0 0 0. It should appear on the first, in the first, because of this. So we apply this row operation, exchange R14. But if we exchange row, because it should take the form P inverse BP, if we apply row operation, we need to perform the same operation on the column. So if we exchange R1 R4, R1 R4 exchange, we need to exchange C1 C4. Okay, simultaneously we need to exchange. So exchanging first row will give us this thing 0 0 0 0, and those two are same. After that it is 0 1 0 0. But again, if we exchange those column, what will we get? It is 0 0 and 0 0 here. Uh, there is 0 1 and there is 0 0. So we get this column, and now it is 0 0 and it is 1 0, and everything in between is fixed, 0 1 0 0. Similarly, now what can we see, that if it is matching with A or not? So the problem is we need this second one on the first second column, right? So again we can perform those row exchange. So we perform R, that is R2 is exchanged with R3, so it will automatically exchange C2 C3, because we need those type of symmetric operation. If we apply some row operation, then inverse operation, which is again a similar exchange, need to be performed. Okay. So R2 R3. So second and third row means it will make it 0 0 1 0 on the third row and 1 0 0 0 on the second. So now again we need to exchange those two things. So it is in between, it will be 1 0 0 0, and it is 0 0 here, 0 1 here, and after that 1 0 0 0, and other are fixed, 0 0 0 0. Oh, there was oh, sorry. So R2 and R3 are exchanged. Okay, there was Actually 0 1 0 1 0. Sorry, it is 0 0 0 1. So it is 0 1. Sorry, 0 1 0 0, because we need to exchange those two columns, and this will give us this. Now it is, so now we can see that this is actually the matrix A. Therefore, we have applied those operation. First operation, if we denote it by some E1, then it is B times E inverse. Maybe this column exchange is denoted by E1. So explicitly this E1 will look like this matrix. It is exchanging first and fourth column. So exchanging first and fourth column of identity, it is same as 0 0 0 1 and 1 0 0 0. Similarly, second is 0 1 0 0 0 0 1 0. We have exchanged first and fourth column. So it is, maybe the correct notation is exchange matrix E14, and this is actually E14 inverse. Similarly, we have exchanged second and third column, which is same as performing E23, and this is E23 inverse. So those gives you actually A. Therefore, the choice of P is this. So A can be written as P inverse BP, where P is same as this E14 E23. So clear that those two matrices A and B are actually similar matrices. Therefore, we can write A as P inverse BP. There exists invertible matrix. We have already found that invertible matrix such that A is P inverse BP. So this is also correct. So let me solve another few problems. Okay. So it is from Hoffman-Kunz. So question number 1 here, there are two linear transformation on C2. So T belongs to linear operator, that is T is a linear operator on C2, and T is defined by this T of x1 comma x2. This is actually x1 comma 0, and there are two bases. B is standard basis. So standard basis means it is standard basis in C2 means 1001, and maybe we can denote it by E1, and B dash, it is alpha 1 alpha 2, where alpha 1 is 1 comma I and alpha 2 is minus I comma 2. The question is what is the matrix representation of T with respect to B dash and B. Sorry, B and B dash with respect to B dash. And there are also several questions. For example, matrix representation with respect to B dash. T with respect to B dash, that is B dash B. Just a minute. Okay, so there are a few problems like this. We may solve those kind of problems. So instead of solving all those things, let me solve only the first problem. So here B is this 1001. Those are the usual standard coordinates. So T of we can write T, coordinate of 10 with respect to standard basis B. This is actually 10, right? Similarly, coordinate of 01 with respect to the standard basis, this is also 01. So we can see T uh, applied on 10, the B dash applied on 10, sorry, not like this. There should be some pattern. So let me write in this way: T applied on 10, this is same as the projection on the first coordinate, it is 10, and similarly T applied on 01, this is same as the second thing, which is uh, the first coordinate projection, which is 0, 0. Now we can see that uh, this 10 can be written as linear combination of those 1 comma 1 I. This is easy, that this is 0 times alpha 1 plus 0 times alpha 2. But we need to write 10 as linear combination of 1 I minus I. So those type of problem can be solved using this again solution of those equations. That is, we need to write 10 as linear combination of 1I minus 1. So to solve, we again perform row reduction. This is same as R2 minus IR1, which gives us 1 minus 1, 1, and this is 0, plus I, that is 2 plus I, that is minus I. Okay, so now 1 by 2 plus I times R2. This gives us 0, 1 here, and minus I by 2 plus I, and 1 here, 1 minus 1 are here. Now we solve as simply R1 plus R2. This will make identity on the left side, and it is 1 minus I by 2 plus I, minus I by 2 plus I. So the coordinate, it is actually easy to solve. So the solution will be, so solution is of this thing is 1 minus I by 2 plus I and minus I by 2 plus I. But we can explicitly write just multiply by conjugate. So it is multiplying by 2 minus I, it will give 2 square uh, minus I square, right, which is plus 5. So we get plus 5 here, and above it is uh, minus of 2 minus I, so minus 2 and plus I, so minus 2 plus I by 5, so 5 It is 3 plus I by 5. So this should be the linear combination. So 3 plus I by 5 minus 2 plus I by 5. So 3 plus I by 5 and then minus 2 plus I by 5. So this should be the linear combination which will give us 1 0. So you can see T applied on 1 0 is there. So this T with respect to this B dash, that is on the range we are writing with respect to B dash, and on the domain we are writing with respect to B. So it can be written as 3. So those rows will be in the first column, 3 plus I by 5 minus 2 plus I by 5. Similarly, those two things will be in the second column, 0. So this should be the correct matrix representation if I have not done any mistake. Similarly, you can find solution of other problems, similar kind of problems, matrix representations. Now for any interesting. Let me solve another matrix representation problem. So suppose consider the linear functional trace, which so the space is M cross n cross n matrices, and we are taking linear functional which sends tr denoted by tr, which sends mn cross n to the field f. So tr of aij, this matrix, it is simply trace is defined as sum of diagonals element. So this is given linear functional. Now the question is, what is the matrix representation? Representation with respect to that standard matrices, which is, we know that if we denote maybe what is the notation for elementary matrices, so maybe it is also E, but I have earlier denoted something by E. It should, I think there should be other notation, but here E denotes those kind of things. So let me define something. So Eij, the matrix Eij here, it defines this is maybe this notation, it is okay. Eij, this matrix belongs to Mn plus n, whose only non-zero entry is 1 at ijth, that is ijth place. It is only ijth entry is non-zero, which is 1, and other entries are 0. So matrix representation with respect to B, comma B dash, where B is this Eij, and there should be an ordering. For example, maybe instead of solving this general case, let me solve for n equal to 2. So it is given as E11, E12, E21 and E2. This ordering is given. First, it is similar to numerical order 11, 12, then 21, 22. And B dash is simply because there is nothing, the field is generated by 1. So this is singleton set 1. We need to find matrix representation of this transformation or linear function. So here we can see TR of E11. This is same as only first 1 it is same as TR of 1000, which is same as 1, right? Similarly, TR of E22 is same as sorry 1 2. It means trace of 1 2 means 1th entry only non-zero. Everything is so it is 0 because trace is sum of the diagonal, which is 0. Similarly, you can see trace of 2 1. This is also 0. Trace of E22. This is also 0. This is non-zero. This is actually 1 because it is 0 0 0 1 that matrix and last entry is 1. So diagonal sum of diagonal is 1. Now we need to find transformation matrix, that is matrix representation of this trace transformation. So with respect to B and B dash is 1, so we can see that it is combination of 1, so we put 1 on the first column. Similarly 0 on the second column, and there it is 0, so 0 again and 1. So this will be the correct matrix representation. Just see what is happening if we apply the transformation on the basis element. Okay, so left side basis element are this, and right side this 1 can be written as 1 times 1. This is 0 times 1, so 1 times 1, so we have put in the first place, and 0 times 1 we have put in the, we are taking coefficient of the basis entries. So this will be the correct matrix representation. So similarly, any matrix representation problem can be solved in this manner. Another thing I should say that rank of any non-zero linear functional is always 1, because we can see here also it is 1. If it is non-zero, it because if it is non-zero, there is C in the range, there is some C in the range, and if C is there, 1 by, suppose V goes to C, then 1 by C times V goes to 1. And similarly, for if you now take any, suppose this is C0, and now for any K, you simply multiply with K. So this goes to K. So you can see it is actually rank is always 1, the rank of linear functional if it is non-zero. And you can also conclude that nullity is dimension minus 1. Okay. So if there is any question you may ask, it's time to stop here. Okay, Anandi. Okay, welcome. Okay, if there is no question, let me stop here. Thank you.